Hey guys, how's it going? In this video, I'm going to go through this Leetcode number 338, counting bit. This problem is listed as easy, but I don't think that's so easy of a problem. I think it's a bit tricky actually. This problem was asked by Google and Adobe in the past 6 months. So what this is asking is to count the number ones in the binary representation of a number. So let's say if you're given an input of n of 2, and we have to go all the way from 0, 1, and 2, and then find their binary representation and then count the number of ones in that representation. So, for example, in here, the binary equivalent for number of 0 is 0, and 1 is for 1, 1, 0 is for 2. So as you can see, there are 1 here, and also there's a 1 here as well. So what we need to return is the number ones. So the first one has no ones, so that's why it's 0, and the next two has 2 ones. That's why we have to input 1 and 1 in here. For the second example, n is 5, and we have to go all the way for numbers, the natural numbers, all the way from 0 to 5, right? So 0, 1, 2, 3, 4, 5. And this is the binary representation. We have to count the number of ones in this binary representation. For example, the binary representation for number 5 is 101. So there are 2 ones in there. That's why we have put 2 in there. So let's walk through the algorithm to see how can we tackle this problem. The first thing I did was to list out the binary representation all the way from 0 to 16. Okay, so this is the binary representation, and then I count how many ones in there. And then as you can see, first one has 0 ones, and all the way to 1, 2, 3, and for example, this one has 3 ones, right? So because it's 0, 0, 1, 1, 1 for a number of 7. And then after that, you kind of find a pattern, right? When you divide this number in groups, right? So this first group has only 1 number, second group has only 1 number, the third group has 2 numbers, fourth group has 4 numbers. The next group has the 5. It has 1, 2, 3, 4, 5, 6, 7, 8 numbers. So the way that I divide these groups by their significant bit or leading ones. Okay, and as you can see, the leading ones over here, over here, over here, over here, and the leading ones over here. So they are in the same column, right? Over here, so they all have the same leading ones until it jumps to the next digit where the significant bit is on the next digit. So for example, in here, 16 is represented by 1, 0, 0, 0, 0. And after we divide it by each groups, and then we kind of can use the dynamic programming approach to build up the array that we need to return, right? So, the thinking process is, let's say, 1 can be represented by 2 to the power of 0, 2 can be represented by 2 to the power of 1 plus 0, and 3 is equal to 2 to the power of 2 plus 1, and 4 is equal to 2 to the power of 2. So the leading bit increased by 1 in here. And then for this chunk, it's all around 2 to the power of 2, right? So for example, 5 is equal to 2 to the power of 2 plus 1, and the next block is 2 to the power of 3 plus something, right? For example, 2 to the power of 3 plus 6 is 14. And then we can use that relationship to build up our dynamic programming approach. For example, let's continue this example. So 2 to the power of 3 plus 6. The number of leading ones, not leading ones, the number of ones is 3. And that number can be represented by A plus 6. So the number of ones in 8 equals to 1. And number of 1 in 6. And then we have done that earlier, right? We can look back to the dynamic array that we had before. So dp of 6 equals to 2. And dp of 6 is equal to dp of 4 plus dp of 2. And dp of 4 is always 1. So as you can see the pattern, right? dp of 4 equal to 1, dp of 8 equal to 1, dp of 16 equal to 1, right? So they are all, like for example, dp of 4 equals to 2 to the power 2, a is equal to 2 to the power 4, 2 to the power 3, etc. And then we plus something. So this is our dynamic programming relationship, right? So we can look back to the calculation we had before by using the current significant bit plus a fraction. Okay, and yeah, so this is the main idea to solve this problem. And at this point, feel free to pause the video and try to solve it yourself. And then I will walk through my implementation in Python. Okay, now this is the implementation. And first, I have some two edge cases. So when n is equal to 0, n equal to 1, I'm going to return these two lists, which is 1 and 1 and 0 and 1. And now we have a DP array, which stands for dynamic programming. I initialize the array to be none and plus the number of possible elements in this array. So for example, I need an n plus 1 because we are counting natural numbers. So it's starting from 0. That's why I need the plus 1. And the dp of 0 and dp of 1 equals 0 and 1. So basically, this is a two building block over here. And then what we can do is to have a significant bit keep track of our. So remember, the number can be represented by a significant bit plus a fraction, not a fraction, plus a remainder. So I have an S bit in here to keep track of the current significant bit. The first one is 0, next one is going to be 4, third one will be, going to be 8, and then 16 and 32, etc. And then for I, goes from the range of 2 to n. Because 0 and 1 we have already dealt with them, right? So the next one will be the second one. Second, 2, 3, 4, 5, 6, all the way to n. So here we check whether the significant bit is current, right? So if the 2 times the current significant bit is less than or equal to the current number, and we are safe to increase the current significant bit by 2, multiplied by the current significant by 2. Okay, so basically we want to see which block they are in, right? So for example, the current block is A for this block. So this one is 4, and this block is going to be 2, right? So basically this is that checking, right? Check if that's still current significant bit. Is that current or not? And now we can decompose the number. So basically I is equal to two parts that we talk about. One is the significant bit, and the one is the remain. And we can rearrange the term, become remain equal to the right I minus the significant bit if the remain equal to 0, and the dp of that will be equal to 1. Basically, this one is for this line over here, this line over here, this line over here, and this line over here, also this line over here. Account for the dp at the significant bit is always 1, right? So because it's 16 equal to the 2, 1, 0, 0, 0, 0, for example, and a is equal to 1, 0, 0, 0. And that's why at each of those points, dp is always equal to 1. And then for other points, we can decompose the dp by the dp at a significant bit plus the remain. For example, 12 equal to dp of 8 plus dp of 4. Right, so we build up our dp array. Let's run it. See, it works and it's pretty efficient. For time complexity, it's going to be big O n, and the reason why is it comes from this for loop. And for space complexity is big O1. We didn't use any extra space. dp is the only array that we're working with, and that's exactly the array that we return at the end. So this is the end of the solution. I hope you find this is helpful. If it is, please like and subscribe. And Don't forget, don't trust this, try yourself. Thank you so much for watching. See you next one.